Hello. So, the next thing that we need to learn about in this space topic is the Big Bang Theory. But sort of before we do that, there's a couple of things that we need to understand first of all. Okay, so I've just made a wee note here. This corresponds, by the way, to page 34 in your notes. But there's two main bits of evidence for the Big Bang Theory that you do need to know. This is a very common exam question, actually, just to name the two bits of evidence for it. One of them is redshift, and one of them is cosmic microwave background radiation, or CMBR for short. But in exams, they don't allow you just to write CMBR. You need to write it out in full. Anyway, redshift we're going to be looking at first of all, but in order to understand redshift, we need to understand something called the Doppler effect. And in order to understand the Doppler effect, we need to know a little bit about waves. Okay, so today really all I want us to look at is like the background information for redshift, and then we'll go on and we'll do a little bit more on that next lesson. Okay, so let's look at waves first of all, because in order to understand redshift, you need to know about the Doppler effect. In order to understand the Doppler effect, you need to know a little bit about waves. So with waves, you would have done a little, and I do mean only a little bit on this, in year 10 physics, if you remember back to that. Now, generally, whenever we're sketching a wave, we would sketch it sort of like that, okay? And the length of one wave is called the wavelength, and we use the symbol lambda for it, and the wavelength is really from one peak to the next peak. So that is the symbol lambda. Okay, so that just means wavelength. So we would draw waves like that, and one wave is just one of these. Another way you could mark it on would be like from trough to trough, or you can mark like from here to here. Now, different waves have different properties. If we're thinking about sound waves, first of all, okay, if we had a sound wave and it was a much higher pitch, then the wavelength is much shorter. If you have a sound and it is like really high pitched, then that means there's way more waves being produced every second. It's a higher frequency is how we would properly say that. So like in the amount of time that we have here, compared to here in this one, there's more waves in that same amount of time as there is in this one. So this one would be a higher pitch, all right? So higher, I'm blocking my thing, higher frequency, which is a higher pitch if we're talking about sound. Okay. Now, if we had a sound that was a lower pitch, then that means there's way less waves getting produced every second. So we would have a much longer wavelength. So we would have, maybe a bit dramatic, but something like that. So this is a lower frequency, and that means it's a lower pitch, like a really deep sound. Now, this is what, like, I would sort of think of this as being like the side-on view of particles. If we were to think as if we were looking down on this, so if we had something that was producing a noise, so say I had this point here and it was producing a sound, it doesn't just produce sound in one direction, okay? It produces sound, and that sound comes out everywhere. And the way that we tend to draw that in diagrams is with these little concentric circles. Now, these lines that I'm drawing now, oh, that's terrible. They're as if we're looking down on this wave. So like these lines here are all the peaks of the waves, if that makes sense. And in the wee gap, in the center of the gap, would be all the troughs. So like these, 1, 2, 3, would be the equivalent of 1, 2, 3. Okay, so let's think if we had our higher frequency one, then that's going to be your sound with loads and loads and loads of waves really close together. because you're getting more waves produced every second with a higher pitch. So it's like this is spitting out waves much quicker, and they're all really close together. So this is the higher frequency, which is the higher pitch. Same again, if we had a lower frequency, that's going to be really spread out waves, because it's like taking its sweet time to produce these waves, and they're coming out really slowly, and that leads to a lower pitch. So lower frequency, as in they're not being produced as frequently, so lower pitch. Right, I've been talking there about sound waves, and the reason for that is that I think they're easier for us to imagine what's going on, especially with the pitch and the frequency and all that, because we know about higher pitch and lower pitch sounds. Like we can, I'm going to say visualize, but you know what I mean. We sort of know a bit about that, about what's going on with that already. Okay, now with sound waves, technically I shouldn't really have drawn it this shape, but anyway, you can show a sound wave in that shape. Other types of waves are light waves. Now, it's harder for us to visualize the change in frequency with light waves, and if we think about light, white light is all the different colors of the spectrum joined together. So red, orange, yellow, green, blue, indigo, violet. And these, every one of these colors all has a different frequency. So violet is the higher or the highest frequency of wave. So that means it has the, like if we think back up to here with the higher frequency, a shorter wavelength. So shorter wavelength, and its peaks are all squashed up. So it correlates to this one here. Okay. With red, it's the lowest frequency. So that means it has a longer wavelength, and its peaks are more spread out. So it correlates to this one. Maybe draw those in there. So this one would look all squashed up, and this one is going to look all spread out. Okay, so we need to know that. We need to know that the violet end of the spectrum is the highest frequency, with the, that means the wavelength is the shortest, so the peaks are all squashed up, which if we are drawing this type of diagram would look like that. And the red end of the spectrum is the lowest frequency, so that means the waves that are produced there have a longer wavelength, and the peaks are more spread out. And if we were drawing our diagram like this, then it's going to look more like that. Now, I know this is really professional looking, but I did actually spend a worrying amount of time cutting out all these circles, but I'm going to try and use this to demonstrate something really cool that happens. So just to remind you what on earth this actually is, this here, so I've done this like purpley blob, right? So it's like a point source really is how we would refer to that, and it's producing waves. Let's say at the start it's producing sound waves, okay? And then these lines here all just relate or correlate to the peaks of the wave, right? So you've got a trough here and a peak and a trough and a peak and a trough and a peak and a trough and a peak, right? So these are the waves that are being produced, and this here, so the distance between these correlates to the wavelength of the waves. Now if we think back to what we know that if the waves are more squashed up, if we're talking about sound, then that means we have a higher pitched sound. And if the waves are all spread out, then that means that is going to be a lower pitch sound. Okay, now here is the cool thing. So here is the cool thing. Here's you, expertly made, I must say. Oh, hang on, the dog. Right, so here's you standing here, and we have something here which is emitting a sound. So every whatever time, let's say every 10th of a second, it emits a sound wave, right? So here's one, here's another one, here's another one, here's another one. And they're moving outwards from the source. Now, if this source is moving towards you, then by the time it gets over here to emit another wave, it's like these ones sort of catch up with themselves. So I'm going to slide this across towards the person to try and show you what actually ends up happening. Everyone keep your fingers crossed that it works. So if I move this over towards the person, let's see. Oh, it's not even going to move. Oh, here we go. It totally worked. Right, okay. So I'm not going to touch it. I'm very excited. So see, because this is emitting the waves at like at a constant rate, but it's moving over this way, by the time it emits the next one, this end of them all get bunched up together, and this end gets spread out because it's moved away from where it originally was whenever it emitted the last wave. I'm doing a terrible job explaining this. Hopefully my little demonstration worked or made sense to you. So let's think back to what that means in terms of the sound. So if this is you standing here and we have something and it's moving over towards you, then that means that the sound that you hear has smaller wavelengths than the original sound actually had, which means that you hear it, if you remember back to this, you hear it as a higher pitch. And if you are standing over here, so if you were here and the sound was moving away from you, the sound waves that you hear actually have a longer wavelength than the sound waves that were emitted, and that means you hear it as a lower pitch, right? I'm going to go over that one more time. So if you're standing somewhere and an object is moving over towards you, the sound that you hear has a wavelength which is shorter than the source is actually emitting. And if you're standing over here, and the sound wave is moving, or the sound thing that's producing the sound is moving away from you, the sound that you hear has a longer wavelength than the actual object is emitting. Now, one way that you will have heard this before is like when a car goes past or a motorbike goes past, like in the Formula 1 car especially, you notice it. So I'm going to play you a little clip of that now. Right, so this is a clip of a MotoGP rider coming towards me and driving away whenever I went to see it ages ago. So let me get my sound up, and you should hear, as the bike is coming towards me, you hear it as a higher pitch, and as it's going away, you should hear it as a lower pitch. So let's see. I'm going to play it again. I'll turn the sound down. That was really loud. Okay, so coming towards me, high, going away, low. Isn't that cool? Don't deny it. Okay, let me get rid of this. Now, here is where it gets even cooler. I know, hard to believe, but the exact same thing happens with light sources. So before we think about it, let me get back this and show you. I'm really scared I'm going to mess this up, so I'm going to just hold this underneath here. So if you remember with light, the highest frequency was the violet light, which means it has the shorter wavelengths and the peaks are all squashed up. And the red end of the spectrum is the lowest frequency, meaning those waves have a longer wavelength and the peaks are more spread out. Okay, keep that in your head. So if you are standing here and a source that is emitting light, so say a car with its headlights on, right? If a car with its headlights on is coming towards you, now the car isn't traveling that fast, so you don't actually see this, but strictly speaking, it's still happening. So this car headlight would be emitting light of a certain wavelength, but as it moves towards you, the waves all get squashed up So you see it at a higher frequency or a shorter wavelength, which is towards the violet end of the spectrum. So the light that you see here would be technically slightly more blue-violet than the light that is actually getting emitted. Right? Cool. If you're standing over here and the light source is moving away from you, then the waves that you see have a longer wavelength than the source was actually emitting. And if you remember, the longer wavelength side was the red end of the spectrum. So the light that you're seeing here is redder than the original source is giving out. Now, in everyday life, because the objects on Earth are not moving that quickly, you don't actually see any visible difference. But what happens is whenever scientists observe light that is coming from distant galaxies, what they have noticed is that the light that they see has all been red shifted. And red shifted means like this, like the light that they know what pattern of light they should be getting, and we'll look at that a little bit more next lesson, but they know what the light should look like coming from a galaxy. And what they find is they get the exact same pattern, but it's all been red shifted, and red shifted means shifted towards the red end of the spectrum, which is like this situation where the object is moving away from you, and the light that you see is redder than the original source was given out. And if you were standing here and something was moving towards you, the term that we would use for that is blue shifted, because the light that you see is shifted towards the blue end of the spectrum. Okay, so here's us on Earth. Here is a distant galaxy. Because the light that we see coming from that galaxy has been red shifted, it is all appearing redder than it should. That means that the galaxy must be moving away from us. And what is even cooler is that that happens no matter what direction you look in. So it's not just like everything over there is moving away from us. It's that if everything over there is moving away, everything there is moving away, everything there is moving away, etc. Right? You get the point. So absolutely everything is moving away, which means that if you go backwards, it must have all originally come from one point. And that is the redshift evidence for the Big Bang. Okay, now we will be looking a little bit more on that next lesson, but I just wanted to make sure that you understood the Doppler effect, and again, to do that you needed to understand the waves. Now, there is a YouTube video that I really like for the Doppler effect. It does it. Oh, I blew my person away. But it does this much clearer than I have done. Don't think I did too bad a job, but I am going to link it here, and I would like you to watch that now, please. Okay, see ya.